Assalamualaikum and good day to all of you. We are now moving into a new chapter, chapter 6. In chapter 6, we are going to discuss the method of Laplace transforms. Laplace transforms are widely used in electrical engineering and mechanical engineering. It has many applications in the study of circuit systems, mechanical systems, image processing, avionics, to see a few. The method of Laplace transform was developed by a French mathematician named Pierre-Simon Laplace. The Laplace transform method is applied in solving initial value problems of nth-order linear differential equations with constant coefficients. The method of Laplace transform transforms differential equations into algebraic equations which are easier to be solved. In other words, to find the solution of the differential equations, we can get it by solving the algebraic equations. Before we go into the details of how to apply the method of Laplace transforms, let us firstly understand the definition of Laplace transforms. Let us begin by considering a function of two variables, f of xy. Now suppose f of xy is equals to xy. Now let's see what happens when we evaluate the definite integral xy with respect to x, where the lower limit is given by 2 and the upper limit of integration is given by 4. Okay, so this is the work of the integration. When we evaluate the integral of xy with respect to x, we are considering x as the variable, taking y as a constant. So when we integrate x with respect to x, the answer is x squared over 2 and multiplied by the constant y. Now we have to substitute the value of the upper limit, which is 4, into the x. So 4 squared is 16. 16 divided by 2 is 8. So 8 multiplied by y gives the first term 8y. Minus the second term can be obtained by substituting x with the lower limit 2. So 2 squared is 4. 4 divided by 2 is 2. 2 times y is 2y. 8y minus 2y, the answer is equals to 6y. So what we can see is that when we evaluate this definite integral with respect to x, taking x as a variable and y is kept as a constant, the answer appears in terms of y. So we say the definite integral has transformed the function f of xy into a function of the variable y. That is, for any function of two variables x and y, if we integrate with respect to x from a to b, the answer will definitely appear in terms of y, because y has been taken as a constant. Using the same idea in mind, let us understand what happens when we evaluate a definite integral of a function of two variables s and t. Suppose the integration is formed as follows: integration from 0 to infinity e to the minus st f of t dt. So when we evaluate this integral, we are taking t as a number which runs from 0 to infinity. In other words, t is always positive, t larger than or equals to 0. And in this integrand, t has been considered as a variable, whereas s has been taken as a constant because we are integrating with respect to t. So when we evaluate this definite integral, we expect the answer will certainly be in terms of s, which we write it as capital F of s. So the function f of s of the variable s is known as the Laplace transform of f of t. And the way we write the Laplace transform of f of t is like this. We denote it by writing down capital letter L, open curly bracket, f of t, close curly bracket. So Laplace transform of f of t. Let us look at the definition of the Laplace transform. Let f of t be a function defined for t larger than or equals to 0. Then the integral Laplace transform of f of t is equals to integration from 0 to infinity e to the minus st f of t dt is equals to fs. Okay, so this definition is said to be the Laplace transform of f of t provided the integral converges. So the Laplace transform f of t is equals to fs, and to get from this part to that part, we need to evaluate this integration. From the previous slide, we have seen this expression, Laplace transform of f of t is equals to fs. So the function f in terms of t is the function that needs to be transformed. So we write Laplace transform of f of t. Now once the function has been transformed, the answer will be in s. So we write fs. See the difference between these two f's. We use small letter f to denote the function that needs to be transformed, and once the function has been transformed, we use the corresponding capital letter F, f of s. It is not necessary to use the letter f to represent the function that needs to be transformed. We can even use other alphabets. For example, if we want to find the Laplace transform of y of t, meaning we want to get the transform of this function y in terms of t, the answer will be written as capital Y of s. So small letter y denotes the function that needs to be transformed, and once the function has been transformed, we use the corresponding capital letter y. Another example, suppose h represents the function that needs to be transformed. So once the function h of t has been transformed, the answer will be in s. So we use a capital letter H to denote its Laplace transform. Another example, suppose we are using I as the alphabet to represent the function that need to be transformed. Usually I represent current. So when we find the Laplace transform of I of t, the answer will be I of s. And we use capital letter I to denote the function that has been transformed. We are going to learn how to use the definition of the Laplace transform to find the Laplace transform of some basic functions. Here is an example of a question. We are asked to use the definition of the Laplace transform to find the Laplace transform of e to the power of at. So in this question, f of t is given by e to the power of at, where a is a constant. So how do you find the Laplace transform of e to the power of at? We are going to start by referring to the definition of the Laplace transform. Laplace transform f of t is equal to the integral from 0 to infinity e to the minus st f of t dt. So since in this question f of t is given by e to the power of at, what we are going to do is to substitute this f of t by e to the power of at in the definition of the Laplace transform. So this is the work. Laplace transform of the given function f of t, which is e to the at, is equals to the integral from 0 to infinity e to the minus st ft now replaced by e to the power of at dt. Okay, so this is an integral where we have to evaluate it with respect to t, so s will be treated as a constant. So both a and s are constants. Notice that this is an improper integral. So to evaluate this improper integral, we are going to replace this infinity by a finite value b. So do this integral and then take the limit of this result as b goes to infinity. So this integral is said to be convergent if this limit exists. In other words, this limit is a finite number, and this integral is said to be divergent if this limit does not exist. So let us now focus on evaluating this integral first. Notice that for this power of e, t is a common factor, so take the t out. And then between these two, -1 is a common number, so take -1 out. Okay, so what is the integration of this exponential function with respect to t? The answer is very simple. We just write down the same exponential function, divide by the constant that appears as the power of the e. So you get the answer as e to the negative s minus a t divided by this constant. So divide by negative s minus a. And after that, we have to consider the two limits of integration. The lower limit is 0, the upper limit is b. So to start with, we are going to substitute t by the upper limit b. So we get the first term, which is given by e to the negative s minus a multiplied by b. Okay, this t replaced by b divided by negative s minus a. Minus, for the second term, t is replaced by 0, e to the power of 0 divided by negative s minus a. Only this term has the b. So we are going to find out what happens when this b goes to infinity. Take note that this expression e to the negative s minus a b divided by negative s minus a will converge to 0 if s minus a is positive. So if this s minus a is positive, this limit will converge to 0. In other words, we say the limit exists. So if the limit exists, that means this integral converges. On the other hand, if we take s minus a to be a negative value, then this limit will diverge. Alright, so this limit does not exist and therefore the integral diverges. So since this limit exists and it goes to 0, so the first term disappears. So what we have now is negative multiplied by negative 1 over s minus a. So the result is 1 over s minus a. So in other words, Laplace transform of e to the power of at is equals to 1 over s minus a on condition that s minus a is positive. On others, we say s has to be larger than a. So that's how we find the Laplace transform of e to the power of at by using the definition of the Laplace transform. Laplace transform of e to the power of at is equals to 1 over s minus a. In the previous slide, I have already discussed with you the existence or non-existence of this limit, or the convergence and divergence of this limit. So let me now show you some examples of how to determine whether this limit exists or not. So suppose s minus a is a positive number. So think of any number which is positive. So the simplest example is s minus a equals to 1, because 1 is a positive number. So substitute s minus a by 1 into this part as well as into this part. So you are getting limit as b equals to infinity e to the power of negative positive 1b, which is e to the negative b, divided by e to the negative positive 1, which is negative 1. But e to the negative b is the same as 1 over e to the power of b. So what is the limit of negative 1 over e to the power of b as b goes to infinity? Okay, from calculus we have learned that the limit e to the power of b as b goes to infinity is infinity. E raised to the power of infinity is always infinity. So this part here will be infinity as b goes to infinity. So now we are going to evaluate the limit of 1 over infinity. 1 over infinity is almost approaching to 0, so we say the limit is equals to 0. So this implies that the limit has a finite value 0, so the limit exists and we see it converges to 0. Let us now consider the case when s minus a is a negative number, a number less than 0. So for example, s minus a is equals to negative 1. Okay, so substitute s minus a by negative 1 into this part and into this part. So we'll get the following: limit as b goes to infinity, e to the minus negative 1b, e to the minus negative 1b divided by negative 1. So we get limit as b goes to infinity, e to the power of positive b, okay, divided by positive 1. So limit e to the power of b as b goes to infinity is equals to infinity. So the limit is infinity, so this implies that the limit does not exist, or we say it diverges. Okay, so from the previous example, we have considered that the limit of this is equals to 0, or in other words, the limit exists on condition that s minus a is larger than 0. This slide shows us the table of Laplace transform. This table has two columns. The heading of the left column is written as f of t. If you look at all the functions listed in the left column, they are all expressed in terms of t, f of t. And these are the functions which are commonly used in differential equations. The heading of the right column is written as Laplace transform of f of t is equals to fs. Let's look at row number 4. F of t is given by e to the power of at. Earlier, we have found the Laplace transform of e to the at by using the definition of the Laplace transform, and the answer for the Laplace transform of e to the at is given by 1 over s minus a. So we can put the result in this table. Example, if f of t is equals to 1, the Laplace transform of 1 can be found by using the definition of the Laplace transform. Replace f of t by the number 1, so Laplace transform of 1 is equals to the integral from 0 to infinity e to the minus st multiplied by 1 dt. After evaluation of the integral, we found out that the answer is 1 over s, and we can place the result in the table. So we can do the same for the other functions. So after evaluating the Laplace transform of the other functions using the definition of the Laplace transform, we get the following results. Transform of t is equals to 1 over s squared. Transform of t to the power of n, where n is a positive integer, is given by n factorial divided by s to the power of n plus 1. Transform of sine kt, where k is a constant, is given by k divided by s squared plus k squared. Laplace transform of cos kt is equals to s over s squared plus k squared. Laplace transform of hyperbolic sine kt, or in other words, we can say Laplace transform of sinh kt is equals to k over s squared minus k squared. And the Laplace transform of the hyperbolic cosine of kt, or Laplace transform of cos kt, is given by s over s squared minus k squared. So we can use the table of Laplace transform to find the Laplace transform of these 8 functions. Let us learn how to use the table of Laplace transform. In this question, we are asked to use the table of Laplace transform to find a Laplace transform of e to the negative 8t. So how to find the Laplace transform of this function? We can refer to the table of Laplace transform, row number 4. If you look at row number 4, this is the function that matches the function given in the problem. So if we compare these two, we can see that a in this question is given by negative 8. So since the transform of e to the at is 1 over s minus a, so we just have to replace this a by negative 8 as given in the question. So the answer for the Laplace transform of e to the minus 8t is equals to 1 over s minus a, where a is negative 8, that is equals to 1 over s plus 8. In the next question requires us to find the Laplace transform of t to the power of 4. Search from the table which of those functions listed in the table matches with this expression t to the power of 4, and we found out that this function matches with the function given at row number 3, transform of t to the power of n, which is given by n factorial divided by s to the power of n plus 1. So if we match these two, we can find that n is equals to 4. So substitute n by 4 in the formula of number 3, so the result will be 4 factorial divided by s to the power of 4 plus 1. But 4 factorial is the same as 4 times 3 times 2 times 1, which is equals to 24. So the answer will be 24 divided by s to the power of 5. In the next question, part C, we are asked to find the Laplace transform of cos 2t. Try to match this function with the one listed in the table, and we find out that this expression here matches the function given in row number 6. Okay, Laplace transform of cos kt is given by s over s squared plus k squared. Comparing these two, we can say that k is equals to 2, so substitute k by 2 in this formula. So Laplace transform of cos 2t is equals to s divided by s squared plus 2 squared. However, 2 squared is equals to 4, therefore the Laplace transform of cos 2t is s over s squared plus 4. The part D, we are asked to find the Laplace transform of sinh 3t. So we are going to look at row number 7, where we are given the Laplace transform of sinh kt. Try to match these two. In this case, we say that k is equal to 3, so substitute k by 3 in this formula. So the answer will be 3 divided by s squared minus 3 squared, or in other words, it is 3 over s squared minus 9. So notice that all the given functions where we want to find its Laplace transform, they are all expressed in terms of t, and the final answer are all expressed in terms of s. Theorem 6.1. Linearity of Laplace transforms. This theorem says that let f of t and g of t be any functions whose Laplace transforms exist, and let a and b be any constants. According to the theorem, the Laplace transform of a multiplied by f of t plus b multiplied by g of t is equals to a multiplied by the Laplace transform of f of t plus b multiplied by the Laplace transform of g of t. So this theorem says that the Laplace transform of the sum of these two terms is equals to the sum of the Laplace transform of each term. Besides that, it also says that the Laplace transform of a constant multiplied by the given function is equals to the constant multiplied by the Laplace transform of that function. We are now going to learn how to apply the linearity of the Laplace transform in answering some of the following problems. In these examples, we are asked to use the table of Laplace transform to find a. Laplace transform of 4 plus 3t to the power of 5 minus 2 sine 7t. In this question, we are asked to find the Laplace transform of a sum of three different functions. And according to the linearity of the Laplace transform, we can split this into a sum of three different Laplace transforms. In other words, Laplace transform of 4 plus 3t to the 5 minus 2 sine 7t is equals to the Laplace transform of 4 plus the Laplace transform of 3t to the power 5 minus the Laplace transform of 2 sine 7t. But we know that 4 is equals to 4 times 1, and therefore the Laplace transform of 4 can be written as 4 multiplied by the Laplace transform of 1. And the Laplace transform of 3t to the power 5 can be written as 3 multiplied by the Laplace transform of t to the power 5. And the Laplace transform of negative 2 sine 7t can be written as negative 2 multiplied by the Laplace transform of sine 7t. So after we have written down this step, we can refer to the table of Laplace transform to get the transform of each of the functions shown here. So what is the transform of 1? Okay, we know from the table, Laplace transform of 1 is equals to 1 over s. So it means that 4 multiplied by 1 over s. And what is the Laplace transform of t to the power of 5? We use this formula. Transform of t to the power of n is n factorial divided by s to the power of n plus 1. Replace n by 5 as given in the question. So it will be 5 factorial divided by s to the power of 5 plus 1. So 5 factorial divided by s to the power of 6. Minus 2 times, now Laplace transform of sine 7t. From the table, there is this formula. Transform of sine kt is k divided by s squared plus k squared. In this question, k is 7, so replace k by 7. So what we are getting is transform of sine 7t is the same as 7 divided by s squared plus 7 squared. 7 squared is 49. So this is already the correct answer for the given question, but if we want to simplify some more, we can write as follows. 4 times 1 over s is 4 over s, plus 3 times the 5 factorial is the same as 5 times 4 times 3 times 2 times 1, which is 120, multiplied by 3 gives 360, divided by s to the power 6, minus 2 multiplied by 7 is 14, 14 divided by s squared plus 49. Question part B. The Laplace transform of 6e to the negative 3t plus t cubed plus 4 everything squared minus 2t minus 5 everything squared. By the linearity of the Laplace transform of the sum of these three terms is equal to the sum of the Laplace transform of each of these terms. For the first term, the Laplace transform of 6e to the negative 3t can be written as 6 multiplied by the Laplace transform of e to the negative 3t. To get the Laplace transform of e to the negative 3t, we apply the formula Laplace transform of e to the at equals 1 over s minus a. In this problem, a is negative 3, so replace a by negative 3 in the formula, we'll get 1 over s minus negative 3. In other words, the Laplace transform of e to the power of negative 3 is the same as 1 over s plus 3. Plus the Laplace transform of t cubed plus 4, everything squared. To square this function, we can take t cubed plus 4 multiplied by t cubed plus 4 and then we multiply term by term to get this expression. Another approach is to apply this formula a plus b squared, where a is t cubed and b is 4. So a squared meaning you have to square the t cubed. T cubed squared is the same as t to the power of 6. 2 times a times b, 2 times t cubed times 4 gives 8t cubed plus b squared, b is 4, so 4 squared is 16. So the Laplace transform of the square of this function is equal to the Laplace transform of this function given here, t to the power of 6 plus 8t cubed plus 16, minus the Laplace transform of the square of 2t minus 5. You can take 2t minus 5, multiply by 2t minus 5 and then multiply term by term to get this expression. Another approach is by applying this formula, a minus b squared is equal to a squared minus 2ab plus b squared, where a in this part here is given by 2t and b is 5. So a squared meaning 2t, you square the 2t, we get 4t squared, minus 2 times 2t times 5 gives negative 20t plus b squared plus 25. Since we have not found the Laplace transform of these functions, we still have to write down the symbol L to denote that we are going now to find the Laplace transform of each of the term in this bracket. The Laplace transform of t to the power of 6 can be found by using the formula Laplace transform of t to the power of n, which is equal to the n factorial divided by s to the power of n plus 1. In this case, n is equal to 6, so we'll get 6 factorial divided by s to the power of 7 as the Laplace transform of t to the power of 6, plus Laplace transform of 8t cubed. Now 8 is a constant, so we can actually evaluate 8 multiplied by the Laplace transform of t cubed. Apply the same formula where now n is equal to 3. So we'll get 8 multiplied by Laplace transform of t cubed is the same as 3 factorial divided by s to the power of 4. Plus the Laplace transform of 16. Now 16 is 16 times 1. So it's the same like evaluating 16 multiplied by the Laplace transform of 1. And we know that the Laplace transform of 1 is 1 over s. Minus the Laplace transform of 4t squared. Okay, so this is the same as minus 4 times the Laplace transform of t squared. So minus 4, Laplace transform of t squared, apply this formula where n is equal to 2. So that will be equals to, Laplace transform of t squared is equal to 2 factorial divided by s cubed. Negative gives positive value for this term. So positive 20 multiplied by the Laplace transform of t. Laplace transform of t from the table of form, the Laplace transform is given by 1 over s squared. So plus 20 times 1 over s squared. Negative, positive gives negative, negative. Laplace transform of 25. 25 is the same as 25 multiplied by 1. So Laplace transform of 1 is 1 over s. So that will give 25 minus 25 multiplied by 1 over s. So this is the result of the Laplace transform of the given function. We can simplify this expression further. For the first term, we get 6 over s plus 3. Now 6 factorial is the same as 6 times 5 times 4 times 3 times 2 times 1, which is equal to 720. So for the second term, is 720 divided by s to the power of 7. 8 multiplied by 6 is 48. So 48 divided by s to the power of 4. 16 times 1 over s is the same as 16 over s. Minus 4 times, now 2 factorial is 2. 4 times 2 is 8. Minus 8 over s cubed. Plus 20 times 1 is 20 divided by s squared. Minus 25 times 1 is 25 divided by s. Okay, so this is the result. And now after checking, we notice that there are two terms with the same denominator s. So we can combine these two, because 16 over s minus 25 over s, that gives negative 9 over s. So the final result is this: the Laplace transform of this given function is equals to 6 over s plus 3 plus 720 over s to the power of 7 plus 48 over s to the power of 4 minus 8s cubed plus 20 over s squared minus 9 over s. Now we are at the last question, part C. Laplace transform of cos t plus pi plus sin squared t. The Laplace transform of the sum of these two terms by the concept of linearity is the same as the sum of the Laplace transform of each of these terms. So that is equals to the Laplace transform of cos t plus pi plus Laplace transform of sin squared t. So in order for us to get the Laplace transform of cos t plus pi, we must firstly apply a trigonometric identity that relates to this expression cos t plus pi. And that trigonometric identity is given as follows: cos a plus b is the same as cos a cos b minus sin a sin b. If you are asked to find the trigonometric identity of cos a minus b, then it will be cos a cos b plus sin a sin b. In this problem, the trigonometric identity for cos t plus pi, where a is equal to t, b is equal to pi, it will be given by cos t cos pi minus sin t sin pi, as shown in this expression here. Transform of sin squared t. What is the trigonometric identity that relates to this function sin squared t? The trigonometric identity for sin squared a is 1 minus cos 2a over 2. So what we have to do is to just replace a by t. So sin squared t can be replaced by 1 minus cos 2t divided by 2. For this expression here, we know cos pi is negative 1 and sin pi is 0. So cos t multiplied by negative 1, that gives negative cos t. So the Laplace transform of negative cos t is the same as negative Laplace transform of cos t. For the second term, it goes to 0 because sin pi is 0. And for this part here, we can factor the constant half. So half multiplied by the Laplace transform of 1 minus cos 2t. So let us now find the Laplace transform of each of these. Now Laplace transform of cos t, k is equals to 1, will be s over s squared plus k squared, a is equals to 1. So the answer for the first term will be negative s over s squared plus 1. Plus a half multiplied by, now the Laplace transform of 1 is 1 over s, minus Laplace transform of cos 2t, now k is equal to 2, that will be s divided by s squared plus 4. So this is the result for the Laplace transform of this given function. So that's the end of our lesson today. In today's lesson, we have learned the definition of the Laplace transform, and we have learned the concept of linearity of the Laplace transform to find the Laplace transform of some functions. So thank you for your attention. So we're going to use what we have learned today to find the inverse Laplace transform in the next section. Thank you.